number 17. So in this class we will discuss about another dynamic routing protocol, which is border gateway protocol. So quick information about the BGP. So BGP is like path vector. So in the previous routing protocol OSPF, we know that that's a link state protocol, but BGP is a path vector. Path vector, why we call it BGP as path vector is, apart from the routing information, we also add some path attributes to each route so that BGP can take a better decision which route needs to be selected and how to forward the packets. So the algorithm used in BGP is like BGP path selection. So it will have some checklist. It will check from top to down. Based on that conditions, it will select the best route. And for the administrative distance value, there are two AD values for BGP, one for eBGP, one for iBGP. So we will discuss what these are in the next slide, but for now remember that there are two AD values for the routes learned through the BGP. For the routes learned in the iBGP, we'll be having the AD value of 200, and for the routes learned through eBGP, we'll have the value of 20. So as the lowest one is preferred, so if the same route learned by the eBGP and iBGP on the same router, it will select the eBGP route because it has the lower AD value. Okay. And then the RFC. So the standards for BGP, if you want to look for additional information, what is the standard, you can look this particular RFC document 4271. It will support both IPv4 and IPv6 routing information. So currently we are just only working on the IPv4. So which protocol it will use to exchange routing information? So in case of OSPF, we have seen that it is just using IP, but BGP it will use the TCP, Transmission Control Protocol, and the port number it will use is 179. So the authentication it will use is MD5. So in OSPF, we have seen OSPF has areas, backbone areas, standard areas, and other types of areas they collected together to exchange the routing information. But in case of BGP, we see autonomous systems. Shortly, we call it as AS. So AS is a like logical boundary to control the route propagation. So BGP is widely used in the internet. So there will be like millions of routes being exchanged using the BGP protocol on the internet. So to have a better control, we can divide BGP into like autonomous systems so that we can, every organization or company can have multiple AS and they can manage it. Okay. So the autonomous system numbers starts from 0 to 65535. So the first one and the last one are reserved. So first one is 0 and the last one is 65535 is reserved. So no one should use these AS numbers in the BGP configuration. Similarly, some range in between 64496 and 6511 also reserved for some documentation purpose. So no one should use this range as well. This is also reserved. No one should use this. So after removing all these reserved, we have two ranges. One is 1 to 64495 and another one is 64512 to 65534. Okay. So you need to remember only these two ranges. Okay. So similar to IPv4 address, we have public and private, right? So public we use it on the internet, and private we use it inside the organization or like non-internet. Similarly, BGP AS numbers also. Public AS, you should use this when you are exchanging route with the internet. If you have a BGP peering with the internet router, you should use the public AS. But if you are using BGP within organization or like non-internet environment, you can use the private AS. So try remember these two ranges only: 126445 and 645.122.655.34. So let's see what is eBGP and iBGP. So in this example, I have total 8 routers. 4 routers, let's say these are R1, R2, R3, R4. They are in AS100. And we have R5, R6, R7, R8 in AS200. Autonomous system 100 and 200. So if you are configuring BGP between the routers in the same autonomous system, we call it as iBGP, internal BGP, R1 to R2. So both are in the same autonomous system 100. So here we have BGP between R2 and R5. So R2 is in the autonomous system 100 and R5 is in the 200. So in this case we call it as external BGP, eBGP. So whatever the routes you learn through eBGP, you will have AD value of 200, and whatever the routes you learn from iBGP, it will have the AD value of 200. So eBGP is 20, iBGP is 200. So when you configure BGP either like iBGP or eBGP, the neighborship forms in like different stages. So the first state is like idle state. So the routes will be exchanged only after this stage. Okay, so this is the first stage, idle stage. In idle stage, router will try to initiate the TCP connection after a start event. So when the start event occurs is whenever you configure the neighbor on this router, when you are trying to configure a neighbor, then that will generate a start event. Then router will try to initiate a TCP connection. Then it will go into the connect state. So in the connect state, it will be waiting for the reply from the neighbor or the peer. Then it will go into the active state. If it does not receive any response, it will still actively trying to make a TCP connection or make contact with the peer or neighbor. Once the TCP connection is established, it will send the open sent message. So in the open sent message, it will check for the configurations. For suppose if this is eBGP, if you have configured 100, 200 here, it will check the AS numbers and the versions, everything, to make sure both are compatible with each other in terms of BGP to establish the connection. So once everything goes fine with this stage, it will go to the open confirm, where it will wait for the keep alive message from the peer. So whenever we have peering between two routers using the BGP, they always send keep alives to make sure the other route is available and reachable. So once it receives the keep alive message, it will go into the established mode. After that, they will keep continue sending routing updates and the keep alive messages just to check if the neighbor is alive. So normally we see whenever we configure the BGP, ideally it should be in the established state so that everything is good. But if you see any other state, means it could be like TCP connection issue or maybe version mismatch issues. So we need to make sure there is a reachability between the peers in terms of TCP connection. Also the configuration is correct. So this is the topology we use for the basic BGP lab. So we have 5 routers, R1, R2, R3, R4 and R5. So we have 2 networks on the R1 side, 1.1.0/24 and 2.2.0/24. And on the R5 side we have another 2, 3.3.0, 4.4.0. So we just want to use BGP to advertise these routes from R1 to R5. So on the way we have, here we have R4, here we have R2 and R3. And similarly, we want to advertise 3.3.0, 4.4.0 from R5 to R1. So we will configure BGP between R1 and R2, R1 and R4, then R2 to R3, R4 to R5. so that all the routers will be running BGP and they will be able to exchange routes from one side to another side. So once we configure the BGP, what will happen is R1 will advertise 1 and 2 networks to R2 and both R4. R2 will forward that in same information to R3. R3 will send it to R5. R4 also will send it to R5. Similarly, same thing happens in the other direction. So that all the routers in the topology will know about the networks 1, 2, 3 and 4. Because when we try to ping from PC1 to PC3, the packet should go all the way to PC3 in the echo request and should come back echo reply. So for this need to work, every router in this topology needs to know how to forward the packets for all the PC networks. So let's see what is the basic BGP configuration. So we go to configuration mode, then we type router BGP. Then we need to give the router autonomous system ID. So in this case, we need to give, for suppose if we are in the R1, so I am using autonomous systems based on the router number just to make it simple. So this one will be AS1, AS2, AS3, AS4, AS5. So what is the local AS number is 1. Then which networks you want to advertise. So currently we have 2 connected networks. So we are using network statement so that BGP will advertise these networks. So the thing to remember is BGP will advertise the routes only if they are present in the route table. If they are not in the route table, BGP won't be able to advertise the routes. Okay. So we use the network commands to inject the routes into the BGP process. Then we are configuring where we want to send this route information. So in this case, we want to send this information to R2 and R4. So the R2 IP on this side is 12.12.2. And which remote AS it is in? So R2 is in remote AS2. Same for the neighbor. The IP for this side is 14.14.2 and remote AS is 4. Okay. So this is the syntax I have provided here. So this is a command special to the lab, the device we are using in the lab. So the device in the lab automatically choosing AD value for eBGP routes as 200, but generally the eBGP AD value should be 280. So for that there is a command we need to apply. So this is telling eBGP routes AD value, this is iBGP, this is for the local routes. So forget about this command for now, but yeah, just apply it in the configuration. Okay. So let's see all the configurations on all the routers. So R1 we reviewed it. Similarly, we do it on the R5 side. So we applied this distance command to correct the AD value on this router. So router BGP 5, because currently this router is in the R5 is AS number is 5 on this topology. Then it has 2 neighbors, one to R3 and R4. So I am giving the neighbor side IP and mentioning the remote AS values. So you can see this command maximum routes. This is the default command, you don't need to give. Router will automatically add that when you give this command. Then we want to inject 2 routes into BGP on R5, about 3 network and the 4 network. So we are using network commands to add routes into BGP. Let's look at R2 configuration. R2 has peering with R1 and R3. So we applied this distance command and then 2 neighbor statements. So we didn't add any network commands here because we don't want to advertise any networks from BGP2. So the only networks we want to advertise in this topology is from R1 we want to advertise 1 and 2, from R5 3 and 4. Okay. These routers in the middle, they just carry that information whatever R1 and R5 is advertising, but they are not adding any new networks into it. So we are not required to add any routes in this topology to establish the connectivity between the PC networks. So same things for R3 and R4. So once we do the BGP configuration, let's verify the routing table. So on R1, so without BGP it should only know about 4 connected routes. So let's see what are all the networks now we can see. So there are 4 connected routes, that's okay. And we have learned 2 routes. The flags we can see here, B and E. So B and E stands for eBGP. So we are learning these routes through eBGP process. Means this router has some BGP configuration with a router in a different autonomous system. So let's see what is the route table is telling this router. So in order to reach 3.3.0 and 4.4.0/24 networks, the next hop is 14.14.2. That means R4. So the route table telling R1 that if you receive any packet with these destinations, you just need to send it to the next hop. So we are also sending the routes from R5. So how this happened is R5 is sending the routes to R4 and R4 is sending to R1. Similarly, same thing should happen from R5 also peering with R3, right? So R5 also should send about this network to R3 and it should come to R2, and R2 also should come forward it to the R1. So but why we only see route pointing in this direction? Why don't we see that we are learning the same thing from R2? Let's check. So to verify what are all the BGP neighbors on a router, you can use the command show IP BGP summary. So this will list all the BGP peerings that currently this router is configured for. So we on R1 we can see there are 2 neighbors, 12.2, which is R2 and R4. This is the version column, so we are using V4. And the autonomous system of remote peers. So for this neighbor is in the autonomous system 2, this is in the autonomous system 4. And R1 autonomous system is local AS number is 1. So they are keep exchanging messages, and we should see the increments if you enter the command multiple times. And the state we can see established. So it has active BGP established with R2 and R4. And the time how long it was up, this BGP. And here you can see how many prefixes means networks, how many networks we received and accepted. So we received 2 networks from each one. So R4 advertised about 3 and 4 network, R2 also 3 and 4. So let's see if the networks are matching. So to verify what are all the routes we are receiving from the neighbor, we can use this command. So on R1 I am using show IP BGP neighbor and the neighbor IP. So in case I am giving R2 and received routes. So with this command we are asking R1 that what are the routes you are receiving from R2. So it is receiving 3 and 4. So I am asking the same thing from R4. So it is also sending 3 and 4. But when we check in the routing table, it is only showing R4 routes. So as you can see the flags beside the routes, there is some difference. See here you only have star, here you have star and greater than symbol. So let's go ahead and check what is star. Star means valid routes. Okay, that looks okay. So both are valid routes. Whatever the routes coming from the R2 and R4, both are valid. And what is the greater than symbols in active? Active means BGP is actively using that route. Means it is using this route only. It is not using this route actively, even though it is a valid route. So it went through the path selection process and it is only selected only one route out of these 2. So if you check this column path, this is AS path. So this is telling where this route is coming from. In this case, from R2 side, it is stating that the route is coming from R2, but before that it came from R autonomous system 3, and before that it came from autonomous system 5. So basically when R2 advertised this route to R1, it is including the information where this route's coming from different autonomous systems. So it is generated in R5 and went to R3 or 3 autonomous system, and then came to autonomous system 2, then it came to the router 1. If you check this is coming from the 5, that's correct, and then it's going to the autonomous system 4 and then directly to R1. So looking at the topology, this is the best path as per BGP path selection process, because BGP will select less number of AS. So if there is a tie between two routes, it will select the route which has less number of AS hops in between. So in this case there is only one AS. Okay, so don't confuse AS with the router. So in single AS you can have multiple routers. Okay, so BGP is looking at this AS path. So whichever has the less number of AS listed in the route, it will choose that. So in this case it will choose these routes. That's why you see the active flag greater than symbol. So that's why BGP only added these routes into the routing table. So if something happens with this link, then obviously there will be only one route available, and this will become the active route, and they will be added into the routing table. But when everything is working fine with these two BGP sessions, the active path will be going this way. Similarly, you can see the same thing on the R5 side. R5 should receive routing information for PC1 and PC2 networks from R3 and R4. So I'm checking for R3. You can see the AS path is 321, so that it is coming from 3 to 1 autonomous systems. For the R4 side, we can see it is just coming from 1 and 4. So this is the preferred path. So we should see active flag, and we should see that route in the routing table. So routes are pointing to the R4 side. There are so many other BGP attributes that BGP go through the path selection process, but in this example it is the tiebreaker is AS path, number of AS paths, AS hops in the path. Okay, so let's verify if the packets are taking the correct routing. So from PC1 we did ping to 3.3.3. What happens when we do the ping? So the expectation is from PC1 echo request should go from PC1 to R1 because it's gateway. Then based on the routing table and BGP outputs, we expect it to go to R5 and then R5, then reach PC3. For the reply, when PC3 is replying with echo reply, PC3 should send it to R5, then to R4, then R1 to PC1. This is what we expect in this topology. So for that we are using a trace command. What trace command will do is it will use the protocol called trace route. It will print all the devices which are routing the packets. Okay, so you don't see switches in this output, only routers you will see where the routing happens. Okay, so when we do the trace to 3.3.3, the next routing hop is 1.1.254, which is PC1 gateway, so which is R1. Then we are saying 14.14.2. In this topology, this is the IP of R4, so the packet went here. Then it is saying like the next hop is 45.45.2, so this is 45.45.2, then 3.3.3. okay, so it is matching whatever the route we have seen. So on every router in this topology, it has the route path to reach this network in this way. So for the replay packet, let's see if it is following the same path. So trace to 1.1. From PC3. So it should go to the gateway, which is here 3.3.4. Then it should go to 45.45.1. 45.45.1 is here. Then 14.14.1 is here. Then PC1 is here. So it is coming in the same direction. Okay. So when the packet goes from PC1 to PC3, if it is going through R1, R4 and R5, and the return packet also coming in the same direction. So this is symmetric routing. Means the original path and the return path are same, so crossing the same devices. If there are any routing issues, sometimes we can see the path, the original path will be in one way, one path, and the reverse will be in a different path. So for suppose if the original packet echo request is going this way and the reply is coming this way, then also ping will work, because it sent a echo reply and received the echo response, but the path for echo request and echo reply is different. So in this case we call it as asymmetric routing. So we don't have asymmetric routing in this topology because echo request and reply going in the same direction, but I just wanted to introduce the asymmetric routing concept. So assignment for this class is build similar topology and verify the connectivity between PC1 to PC3 and PC2 to PC4. Ping should work, and verify the write tables on each router, and verify the BGP status using the show IP BGP summary, and what are the receiving routes from R1 using the command show IP BGP neighbor 12.12.2 received routes. Same for this, and do the same thing for here, and verify what are the valid and best routes on R1 and R5. So in the next class we will discuss about how we can control what routes we want to advertise. Bye for now.